Hello and welcome to this new tutorial. In the previous tutorial we took care of the encoder RNN layer, and in this one we're going to take care of the decoder RNN layer. And we're going to have to do it in 3 steps. First step will be to decode the training set, and that's what we'll do in this tutorial. Second step will be to decode the validation set, and that's what we'll do in the next tutorial. And then eventually we'll be ready to create the decoder RNN layer. So let's take care of the first step in today's tutorial, decoding the training set. So again, we're going to make another function. This architecture is all about making functions, and this function we're going to make is going to be called the decode underscore training underscore set. That way we clearly understand what's going on. Decode training set, and it is going to take a lot of arguments. So let's add them one by one. The first argument is going to be the encoder underscore state, because our decoder is getting the encoder state as input, as part of the input, to proceed to the decoding. And therefore we will need the encoder state that was returned by the previous function encoder RNN layer to proceed to the decoding. Alright, so encoder state. Then the next argument is going to be the decoder cell, and that's basically the cell in the recurrent neural network of the decoder. Then the next argument is going to be the decoder embedded underscore input, and that's basically the inputs on which were applied embedding, and I'm going to explain to you right now what this means. But to do this, the best way is that I go to the TensorFlow website in the embedding section in the programmer's guide. So basically we have a clear explanation here. An embedding is a mapping from discrete objects such as words, and especially words here, we're dealing with words, to vectors of real numbers. So for example, a 300-dimensional embedding for English words, like we're dealing with, could include blue with the following code, the following embedding code. Then blues, the following embedding code. So basically, an embedding is just a mapping from our words to vectors of real numbers, each one encoding uniquely the word associated to it. And so that's very important to work with embeddings when building a sec-to-sec model, because that's basically the kind of format that the decoder is accepting for its inputs. And therefore, I'm going to go back to Python. Well, we need to have our embedded input, and I'm precising that these are the inputs of the decoder. So decoder embedded input, then we're going to take again our sequence length. Then the next one is going to be the decoding underscore scope. So this is pretty technical, and again, to explain that to you, I'm going to go back to TensorFlow on this time the tf.variablescope class by TensorFlow, which I get not in the programmer's guide but in the API R1.4 at the time I'm speaking. So variable scope, what is it? That's basically an advanced data structure that will wrap your TensorFlow variables. And so the next argument here that we're inputting is the decoding scope, but that will be like an object of this variable scope. Alright, so let's go back to Python. And here we are back in Python, decoding scope. Then we have 3 more arguments to go. The next one is output underscore function. So basically that's a function we will use to return the decoder outputs in the end. Then we're going to have our keep prob argument, because again we're going to apply some dropout regularization, and eventually the batch size, because we will work again with batches. Alright, and that's it. So that's a lot of arguments, but no worries, we will try not to get lost. Alright, so the first thing we're going to have to do is get the attention states. So I'm introducing a new variable here, attention underscore states. And how are we going to get them? Well, before getting them, we're going to have to initialize them. And we're going to initialize them as 3-dimensional matrices containing only zeros. And to do that, we have to use the tf.zeros function, like the numpy.zeros function. And inside this function, well, like the numpy zeros function, we have to specify in square brackets the number of lines of this 3-dimensional matrix we want to create, the number of columns, and the number of elements in the 3rd dimension, that is the 3rd axis. So let's take care of the lines first. The lines corresponds to the observations, and therefore, since we're working with batches here, well, we have to create a batch, and therefore the number of lines is going to be the batch size. And so, since batch size is one of our arguments, well, the number of lines here is going to be batch underscore size. All right? Then the number of columns is going to be 1. We only need one column. And for the third dimension, the third axis, well, the number of elements in this third axis is going to be the decoder cell dot output size. The decoder cell output size. All right, so we just initialized our attention state, and now what we have to do is prepare the keys, the values, the functions for the attention. So we're going to get first the attention keys, then the attention values, then the attention score function, then the attention construct function, and all these we will get it in one shot thanks to a very useful TensorFlow function that belongs to the sec2sec submodule from the contrib module, which is prepare attention. So that's exactly what we want. Right now we want to pre-process the training data in order to prepare it to the attention process. So let's get them. First, we said the attention keys, the attention values, the attention score function, the attention construct function, and all these, we're going to get them from TensorFlow, the TensorFlow library, then from the contrib module, and then from this contrib module, the sec2sec submodule. I'm really glad that TensorFlow offers this. This is very practical for all the preprocessing of attention. So sec2sec, and so from the sec2sec submodule, we're going to have to get the prepare underscore attention function, because right now we want to do some preprocessing for the attention process. So the prepare attention function, and here we go for another round of many arguments. The first one is going to be the attention state that we just initialized in the previous line, right here. So attention states, right now they're just initialized as zeros. Attention states, then we're going to have to choose an attention option. So basically you have several options to proceed to the attention process, and one of them, which is the one we're going to choose, is BAHDANAO. So attention option equals badano, and the next argument is going to be the number of units which we get thanks to the decoder cell. So we'll take this decoder cell argument, that is the cell of the decoder, and we'll get its output size, which corresponds here to the number of units in this prepare attention function. So we take our decoder cell and we add the output underscore size. All right, so now that we added everything, I'm just going to say a few words on what exactly these guys are. So the attention keys, that's the keys to be compared with the target states. Then the attention values, that's the values that we'll use to construct the context vectors. I remind that the context is returned by the encoder, and that should be used by the decoder as the first element of the decoding. Then the attention score function is used to compute the similarity between the keys and the target states. And eventually the attention construct function is a function used to build the attention state. So we have all these attention features, and now the next step is to get the training decoder function that will do the decoding of the training set. And so this is a function that we're going to get right now. I'm going to introduce here a new variable that will be this function, and then I'm going to call training underscore decoder underscore function. Sorry again for the long variable names, but that's just to clearly show you what's going on here, so that you have a clear visual at what's going on. So training decoder function, and thank goodness we're going to get it from another function by the sec2sec module of the TensorFlow library, which is the attention decoder fn train function. So you see, I'm not the only one to choose big variable names for all these. TensorFlow does that too. So let's get this function from first the TensorFlow library, then from the contrib module, then from the contrib module we get the sec2sec submodule, and from this sec2sec submodule we get the function we want, which is the attention underscore decoder underscore fn underscore train. And that's the function that will decode the training set. But it can only do it once we prepare correctly the attention, which is what we've just done here in the two previous lines. All right? But now we can get it, and as you can imagine, the attention features that we prepared just before, thanks to the prepare attention function, is going to be the arguments of this attention decoder fn train function. So let's do this. Let's input them one by one. However, we're going to input all of them, but we will input one more, and that will be our first argument here, and that's the encoder state. Encoder underscore state, which I remind we got from the previous function, encoder RNN layer. We got it here thanks to the bidirectional dynamic RNN function, again from the TensorFlow library. So that's this encoder state here, but to get exactly what we want, that is the value of the state, well, we need to get the index 0 of this encoder state variable. All right, so encoder state 0, that's the first argument, and then we're going to have to input all the attention features as the other argument. So let's take care of them one by one. The first one is our attention keys that I remind will be compared to the target states. Then the next argument is our attention underscore values that I remind again are used to construct the context vectors. All right, the next argument is our attention score function that computes the similarity between the keys and the target states. So attention score function. All right, perfect. The next argument is our attention construct function to build the attention state. So there we go, attention underscore construct function. And eventually we have this last argument here, which is the name argument. And this corresponds to a namescope for the decoder function. And the namescope we want here is a TensorFlow namescope, attention, but spelled this way, ATTN underscore dec for decoder and underscore train, that you have to put in quotes. All right, so there we go. We have all our arguments here. And now I think it's really important that we take a step back and explain what's going on, because this is pretty overwhelming. But in order to survive overwhelmingness, well, we need to take a step back. That's very important. So basically what we just did here is that we got an attentional decoder function for the training of our dynamic RNN decoder that we're going to make in 2 tutorials, because in the next one we'll take care of the validation set. But we're doing this for this future dynamic RNN decoder. So now that we did that, we're going to move on to the next step, which is to get the decoder output. So I'm introducing here a new variable, which is decoder output. And this, I'm going to get it from, again, another function by the sec2sec module of TensorFlow, which is the dynamic RNN decoder. So dynamic RNN decoder is a function that is used to get the output, the final state, and the final context state of the decoder. And therefore, since it returns first the decoder output, then the decoder final state, then the decoder final context state, but we're only interested in the decoder output, well, what we have to do before applying this function is add, these underscore and underscore here, because this function that we're going to use returns these 3 elements, but we only need the first one. And if you want, I can even write to you what this returns if you want to have a more clear understanding of what is going on. So the second argument is the decoder final state, and the third argument is the decoder underscore final underscore context underscore state. That's what will be returned by the function, but we only need the decoder output. Therefore, feel free to replace all these by underscores. But for those of you who liked the idea of clearly showing what's going on here, I can even replace this underscore here by the first element returned by this bidirectional dynamic RNN function, which is, again, the encoder output, but which we don't need for the encoding. But for those of you who are interested to see what's going on with the functions we're using, I can still add it here, encoder underscore output. Encoder output, and for the other group of people who doesn't care of seeing everything, if I may say, well, feel free to replace that by an underscore, right? So, but now, not only we have a clear visual at what is going on, but also we will get what we want, which right now is the decoder output. Keep in mind, in short, you can actually write that down. For the encoder, you will only need the encoder state, because that will then go into the decoder. And for the decoder, you will only need the decoder output. The decoder output and not the final state or the final context state. All right, so now let's get this function that will return the decoder output. So this function, we get it from the TensorFlow library, of course, then the contrib module, then the sec to sec submodule, and from the sec to sec submodule, we get the dynamic underscore RNN underscore decoder function. That's the one, dynamic RNN decoder function. And this dynamic RNN decoder function takes several arguments. The first one is the decoder cell, which is one of our arguments of the decode training set function that we're making right now. See, decoder cell here. And that's what we need first for this dynamic RNN decoder function. So decoder cell, then the next argument is going to be our training underscore decoder underscore function that we just got at the previous line, this line here. All right, training decoder function. Then the next argument is going to be the embedded input of our decoder, which is one of the arguments of our decode training set function. This one, decoder embedded input. So third argument here, decoder embedded input. Perfect. Then next argument is the sequence length. Then the next one after that is the scope, which is another of our arguments, and that's the decoding scope here. So decoding underscore scope. All right, and we're done. Then one last step. So let's go back here. Perfect. The final step that we should do here is to apply a final dropout to our decoder output. And therefore, I'm going to introduce a final variable here that I'm going to call decoder underscore output underscore drop out. And now it's going to be simple. We'll just use the dropout function from the NN module by TensorFlow to basically apply dropout to our decoder output that we just got here, with still the keep prob controlling parameter of the dropout rate. All right, so let's get the TensorFlow library first, then the NN module, and from this NN module we get the dropout function that's going to take two arguments. First, the output of the decoder on which we want to apply dropout, decoder output, so decoder underscore output, and the second one, the keep prob parameter controlling the dropout rate. So keep prob and perfect, we just got our decoder output with dropout applied and for the training data. So let's not forget just to return it, return, and now to return it the right way, we're going to use our output function, which is one of our arguments here, output function. And this output function is going to take what we want to return, which is our decoder output dropout. And congratulations, we are just done with this function. I hope that wasn't too overwhelming. I really tried to take a step back several times. I will give you in the resources of this tutorial the links of the TensorFlow pages that I showed you. You have a lot more explanations that I could tell you in one tutorial. So have a look at the resources in this tutorial and hopefully have a better understanding. All right, so we're gonna execute. I'm just seeing the little typo here, output, and this should be all fine. So we're gonna select all these and execute. Perfect, decoding of the training set done. And now we're gonna tackle the decoding of the validation set. The good news is that it's gonna be quite the same as what we just did. So we're just gonna make a copy paste and then we'll have a few things to change, but we'll get quickly to creating the decoder RNN layer in 2 tutorials. Until then, enjoy DeepNLP. Hello and welcome to this new tutorial. In the previous one, we made the decode training set function that decoded the observations of the training set and at the same time returned the output of the decoder. But that was for the observations of the training set, that is, some observations that are going back into the neural network to update the weights and improve the ability of the chatbot to talk like a human. But now, in this tutorial, we're going to make kind of the same function, but for a new kind of observations. These observations are actually the observations of the test set and the validation set. And basically, these are new observations that won't be used for the training. And that's why, as you can see here, I called this code section decoding the test validation set, because the function we're about to make will be used not only to predict the observations of the test set in the end, that is, the answers of the questions we'll be asking to the chatbot in the test phase, part 4, remember, but then also the validation set. And what is the validation set? That's the set we will make during the training also, but we will do some cross-validation technique to keep separately 10% of the training set for cross-validation, which is a technique that keeps a small part of the training data to test the predictive power on new observations. So that's a very useful technique to not only reduce overfitting, but also to improve the accuracy on new observations. And so the function we're about to make right now will be very similar to the one we just made, only there is going to be one fundamental change. It is the function by TensorFlow we're going to use right here. In the previous tutorial, to make the decode training set function, we used the attention decoder fn train function to make this training decoder function. But now, since we'll have to make a test decoder function to, decode the observations of a test set or the validation set, well, this time we won't use the attention decoder fn train function by TensorFlow. We will use another one called the attention decoder fn inference function. Why inference? What does that inference term mean exactly? Well, if you look at the definition on the dictionary, to infer means to deduce logically. And that perfectly makes sense, because once the chatbot is trained, it has a logic inside its brain, and therefore it is able to deduce logically the answers to the questions that is being asked based on the logic it learned during the training. So it understood its own logic during the training, and therefore after the training, on new observations, it will infer the answers to the questions that is being asked. So that's why the name of this new function we're about to use will perfectly make sense here, to decode the test validation set, that is, to decode some new observations that won't be used for the training. We will use the attention decoder fn inference function. And that's the main change we'll have to make here. We will have to make some little other changes, but that's the most fundamental one. All right, so let's do this. Are you ready? We're going to do this efficiently. I'm going to copy this function and paste it here. So first, what we'll have to do is, of course, change the name of the function. So you can either call it decode test set or decode validation set, or decode test validation set, as you want. But since the ultimate goal is to predict the new observations during the test set, that is in part 4, testing the sec-to-sec model, testing the chatbot, well, I would like to call it decode test set. But keep in mind that we will also use this function for the validation set when applying cross-validation during the training. All right, so decode test set. And now this function is going to take almost the same arguments here, but plus 4 new ones that we will have to input between decoder embedded input, and sequence length. So I'm going to add them here. The first one we need to add is the SOS token ID, the start of string token ID, which I'm going to name SOS ID. Then the second one we'll need is going to be the end of string token ID this time. So I'm going to call this one EOS underscore ID. Then the maximum underscore length, which corresponds to the length of the longest answer you can find in the batch, maximum length. And then a final one that we have to add here, which is the total number of words of all the answers. So basically you have to take the answers words to int dictionary, take the length of the dictionary, because in this dictionary we have all the different words as the key identifiers of all the answers text. And therefore later on, this argument that I'm about to add here will be this length of the answers words to int dictionary. But right now I just need to give a name to that, and I'm going to call it num, like number, words. All right, I think that makes sense, that it's a total number of words. We will also use, not in this function, but at some point we will also use the total number of words of the questions, but we will make that difference clear. All right, so that was the 4 new arguments we needed to add. So now the question is, why do we need to add them? That's just because of this new function we will use here. You know, we're not going to use the attention decoder fn train function as we said. We're going to replace it by attention decoder fn infer function, and this attention decoder fn infer function will need these 4 new arguments here. So that's the only reason why we have to add them. Okay, so SOS ID, EOS ID, maximum length, number of words, perfect. Now let's move on to the other lines to see if we need to change anything. So here the attention states, well, of course, again, we will need them, so nothing to change here. Then the attention keys, the attention values, the attention score function, and the attention construct function will also be needed, of course, inside the attention decoder fn infer function. Because, of course, we still need to consider the attention to predict our new observations. The only difference is that these new observations won't be used in the training, that is, they won't be back propagated inside the neural network. But we still need attention because attention is part of the power of the prediction. So that's why we need to keep the attention features here that will be inside this new function. And speaking of this new function, well, that's the fundamental change we need to include here. So first of all, let's not forget to change this variable name. Now we're not going to make a training decoder function, but a test decoder function. And so now let's apply the fundamental change. We're going to make this test decoder function thanks to the attention decoder fn inference function. And this attention decoder fn inference function is still taken from sec to sec, of course, from contrib and from TensorFlow. All right. And now this function is going to take almost the same arguments, but of course, new ones as you understood. So first of all, the first argument it's going to take is not encoder state. Be careful with that one. It's going to be the output function. The output function is needed because we will not return our final test predictions using the output function here. The attention decoder fn inference function allows to input this output function, and therefore instead of using it in the end, we will use it right here. Therefore we have to include it here, and that's why I'm adding right now output function, which is still our argument of our new decode test set function. All right, so let's move on. Let's not forget the comma here. And now let's see which arguments we need to keep here, which arguments we need to remove, and which arguments we need to add. So output function, then encoder state 0, yes, we have to keep it. Attention keys, yes, we have to keep it as well. Attention values, yes. Attention score function, yes. And attention construct function, yes as well. And that's because these are the attention features that we need to keep, because we need to keep the attention part of the neural network of the decoder, because of course that's a part that plays a powerful role into predicting the final outcome. So we have of course to keep the attention to forward propagate the signal and get even more relevant predictions. So we have to keep all the attention features, and then that's where we need to add some arguments. And I'm sure you know which ones we need to add. That's of course the ones we added here as new arguments of our decode testset function. But that's not all. We also need to include this one, which by the way is not exactly the decoder embedded input. This is rather the decoder embeddings matrix that gives us these inputs. So decoder embedding matrix, not to be confused with the decoder embedded input. You'll see when we make the decoder RNN and then the sec-to-sec model, and actually two tutorials, well, we will make the distinction between these two, the decoder embedded input and the decoder embeddings matrix. And the argument here that we'll need to add in this attention decoder FN inference function is the decoder embeddings matrix. By the way, again, I recommend to check out the resources of each lecture, because in each lecture I provide the essential TensorFlow documentation that you have to check out to, if you want, get more details on the essential function we are using. So for example, for this lecture, I will provide the documentation for this attention decoder FN inference function so that you can see more details on each of these arguments, for example, and what it returns and what it does exactly. That's because I cannot provide all the details in the lectures, but you'll have all the details in the TensorFlow documentation. All right, so we're going to add these new arguments for this attention decoder FN inference function, and that starts from this one, decoder embeddings matrix, up to the number of words. So that's the decoder embeddings matrix, the start of string token ID, the end of string token ID, maximum length, and number of words. So let's get all of them. I'm going to copy them, and I'm going to add them efficiently by just pasting them right here. So let's add them one by one. First, decoder embeddings matrix, perfect. Then SOS ID, there we go, EOS ID, and maximum length and total number of words, num words. All right, so now we have our new arguments. That's perfect, but that's not all for this attention decoder FN inference function. We need to change the scope name here, which for the attention decoder FN train function was the attention decoder train code for the scope name. But now we're no longer doing some training, we're doing some inference, meaning that we're predicting the outcomes of new observations that won't be used for the training based on the logic that was learned and understood by the chatbot during its training. And therefore, to specify that we're not in training mode, but instead in inference mode, well, we need to replace this train here by inf. So basically this name scope is the name of the mode of the decoder, whether it is in training mode to train the chatbot on the observations or the inference mode to predict the outcomes of new observations that won't be used for the training. All right, so we got our new mode, attention dec inf, attention decoder inference. That's great, and now we're almost done. We need to change a few things left right here. So we're still going to use the dynamic RNN decoder function to get the final output. But since this final output won't be used for the training, that is, won't be back propagated into the neural network, we can directly call this output, not decoder output, but test predictions, because these are our ultimate predictions, test predictions. And then if you want, you can keep the decoder final state and the decoder final context state, even though we won't be using them for the rest of the implementation. That's only if you want to have a clear visual look at the elements returned by the function you're using. It's okay if you keep them, that's just for clarity. All right, perfect. So test predictions, that's what this decode testset function will return. And now let's change a few things left here in this dynamic RNN decoder function. So first of all, let's align everything like that. Sequence length and scope. All right. And now let's have a look at the arguments one by one. All right. So to get our final test predictions, we're going to use the dynamic RNN decoder function, and we'll need the decoder cell. So we have to keep it here. The next argument, training decoder function, Well, of course, we won't be using the training decoder function this time, but instead the test decoder function. That's the function we just got here thanks to the attention decoder efferent inference function by TensorFlow. So make sure to replace this by test decoder function. And then decoder embedded input and sequence length are only used for the training. They're not used to get the final predictions or the predictions on the cross-validation set. So we can remove them. I'm removing that line here. All right, perfect. And now let's see the last one. Scope equals decoding scope. Yes, we still need that for the test predictions and the validation predictions. So we will keep that, and therefore we are done with these test predictions that we just got. Perfect. Then next line, decoder output dropout. Well, do you think we have to keep it? The answer is of course no, because the dropout is only used for the training to reduce overfitting and improve the accuracy. So that's only for the training and therefore not for the test part, and so we can remove this as well. All right, and finally, return output function decoder output dropout. Well, here you'll probably guess what we have to do. It's actually very simple. Since I told you we're not going to use the output function here in the end to get our test predictions, because we use this output function in the arguments of this attention decoder efferent inference function, well, instead of using it, we will just replace that by what we want to return, and which is directly our test underscore predictions. Perfect. Return test predictions, and now we are done with this new decode test set functions that decode the observations of the test set and the validation set, and that returns the test predictions or the validation predictions. Great. So now we're ready to select this function and execute. Perfect. We now have our decode test set function. So great news. Now we're ready to make the decoder RNN layer, or more simply the decoder RNN. By the way, we called this function encoder RNN layer. I don't want you to have any confusion between the main layers of the sec-to-sec model, that is the encoder layer and the decoder layer, and the sublayers inside each of these models. So in order to avoid any kind of confusion like that, I will just replace this encoder RNN layer name function by simply encoder RNN, so that you understand that we are just building the architecture of the RNN of the encoder, which we sometimes call the main layer of the encoder RNN, but in order not to confuse it with the layers inside the RNN, well, I prefer to call it encoder RNN. I think this will avoid any confusion. And therefore, in the next tutorial, we will make the function that will build the decoder RNN, and we'll use, of course, these two functions, decode training set and decode test set, because we will not only get the training predictions, but also the test predictions for respectively the training set and both the validation set and the test set. So we'll do that in the next tutorial, and until then, enjoy DeepNLP. Hello and welcome to this very exciting tutorial where we will create the decoder RNN as opposed to what we did before when we created the encoder RNN. Remember, in this code section here, we made the encoder RNN function. By the way, I just replaced the previous name encoder RNN layer by encoder RNN at the end of the previous tutorial. And so in today's tutorial, we're going to make another recurrent neural network, which will be this time the recurrent neural network of the decoder. And therefore, let's scroll down back. We're going to make a new function here that we're going to call decoder underscore RNN, the recurrent neural network of the decoder. So if you're ready, let's begin. So this decoder RNN function is going to take several arguments, actually lots of them. So we're going to input them one by one quite quickly now that we are starting to get comfortable with all these different objects. All right, so the first argument is going to be the decoder underscore embedded underscore input. We already covered that. Let's move on to the next one. Then the next one is going to be the decoder embeddings matrix. So again, I will provide the resources in the description of this tutorial if you want to have more details on this. Then the next one is going to be the encoder underscore state, which I remind, that's a very important thing to keep in mind is that it's the output of the encoder, but that becomes the input of the decoder. So encoder state, we will definitely need it for our decoder RNN. Then we're going to take again the total number of words in our corpus of answers. Then sequence length, again, we've already seen that, sequence length. Then the RNN underscore size, which is another one of our previous arguments. Then the number of layers that we called num layers. So that's this time the number of layers we want to have inside the recurrent neural network of our decoder, num layers. Then what else? We're going to need our word to int dictionary, but that can actually be any dictionary. It's just an argument, but that will of course be our answers words to int dictionary that we made in the previous part 1 data preprocessing. Then we're going to apply some dropout again because there are going to be some training in the implementation of this decoder RNN, and therefore we're going to use the keep underscore prob parameter to control the dropout rate. And finally, one last one. Try to guess what it is. It's very important, it's at the heart of any neural network. It is the batch size, because the inputs of neural networks, whether it is in TensorFlow or PyTorch, are into batches. And we need to specify a batch size to choose the size of these batches. All right, so that's it for our arguments. And now let's start implementing this function. So we're going to start with the with syntax of Python, to precise that we're making this decoder RNN in a decoding scope. Remember the decoding scope? I explained that in, I think, 2 tutorials ago. It's a more advanced TensorFlow variable that will contain several data entities. And therefore, what we need to start here is introduce the scope, and we're going to do it this way with TensorFlow. And then from TensorFlow, we're going to get the variable underscore scope. I will put that again in the resources of this lecture. And now in quotes, we're going to input decoding as the decoding underscore scope. All right, now we have to add some colon. And now inside the scope, we're going to make everything happen. All right, so the first thing we need to start with is create our LSTM layer. And so as for my encoder, I'm going to call it LSTM equals, and then exactly the same as our encoder, we're going to get our TensorFlow library. Then from this library, we're going to get the contrib module. Then from the contrib module, we're going to get the RNN submodule. And from this RNN submodule, we're going to get the basic LSTM cell. The basic LSTM cell class that takes as input only one argument, which is the RNN size. Remember, that's exactly what we did here for the encoder. We created the LSTM layer, which was same, an object of the basic LSTM cell class that takes as input the RNN size. Perfect, so we now have our LSTM. And so now that we have our LSTM, what do? Well, it's time to apply some dropout regularization to reduce overfitting and improve the accuracy. And so we're going to introduce the same variable name, LSTM underscore dropout, meaning an LSTM layer on which dropout is applied. So LSTM dropout, and that again will be an object of another class that we used for our encoder. There it is. And so we can basically copy this because it's going to be exactly the same. It is going to be an object of the dropout wrapper that needs to take the previous LSTM layer that we created as an object of the basic LSTM cell class, and that uses the keepProb parameter controlling the dropout rate. So let's do this. Let's paste that here. TF contrib RNN dropout wrapper LSTM input keepProb equals keepProb. Perfect. So now we have our LSTM layer with dropout applied, but that gives us one LSTM layer. And of course, we're not building a kit stuff RNN, we're building a stacked LSTM. And therefore, now we're going to use the multi-RNN cell to stack several LSTM layers with dropout applied. And again, that's exactly what we did for our encoder. So I'm going to simply, copy this line, and just below for our decoder RNN, Well, I'm going to introduce this new variable here that will be our decoder cell. I remind that the decoder cell is what contains the stacked LSTM layers with dropout applied. So that's basically a cell of LSTM layers. And therefore, this decoder cell is going to be the paste of what I just copied. That is an object of the multi-RNN cell taken from the RNN module of the country module from the TensorFlow library, which takes as input the previous LSTM layer on which dropout was applied times the number of layers we want to have in this stacked LSTM layer inside the decoder cell. Then, next step. The next step is actually something new, something we haven't done before. We need to initialize some weights that will be associated to the neurons of the fully connected layers inside our decoder. That is the last layer. And to initialize them, well, first we need to introduce a new variable that I'm calling weights. And we're going to initialize them by using an initializer that is the tf.truncated normal initializer. And that will generate a truncated normal distribution of the weights. This function takes only one argument. We're going to choose standard deviation, which will be 0.1. And to specify this, we need to enter the following argument here, which is std_dev, standard deviation, and that is equal to 0.1. All right, so now we have our fully connected weights initialized. Then, next step. Naturally, after the weights, the next step is to get the biases. So I'm introducing a new variable here, biases, and now, much more simple, we just need to initialize them as zeros, and to do that we use the TensorFlow function that is called zeros_initializer, and just some parentheses with nothing inside. Alright, so now we have our weights, our biases for the fully connected layers. Great, we're ready to move on to the next step. The next step is to make the output function. And so I'm getting it output_function. So I'm introducing a new variable that I choose to have the same name as the argument given in the previous functions, output function. And now we're going to use the classic Python syntax to make a function, which starts with lambda. Then the variable of this function is going to be x, then colon, and what comes after this column is what this function will return. So what this function will return is some fully connected layers that will be used for the last layer of the RNN. You know, the fully connected layer comes at the very end of the recurrent neural network. You have the LSTM cells first, you know, the stacked LSTMs in the cell, but then at the end of the recurrent neural network, you have the fully connected layer. And therefore, that's exactly what we're making right now. We already have our decoder cell composed of the stacked LSTM layers with dropout applied for each one. But now we need to make effectively that fully connected layer. And we're making this with this output function that we're making right now. All right, so let's make that. Good news, we have a TensorFlow function that will do that for us. And so the first thing I'm going to do here is get TensorFlow first, then again the contrib module, and then this time, since we are building the most classic neural network layer, it's not going to be taken from RNN, it's going to be taken from simply layers. Layers, and from layers we get the fully_connected function. All right, and this function now is going to take several arguments. All right, so the first argument is the inputs, and the inputs are, of course, our variable x at this stage. So x here, I will share with you the fully connected function in the resources of this lecture, so check it out. Then the second argument is going to be the number of outputs, and that is the number of words in all the answers, which is numwords here, so numwords. Then the next argument is the activation function, and we'll keep the default value, which is a relu. Then for the normalizer, we won't do any normalization, so we will specify here none. Then eventually we have to enter the scope, which is our decoding underscore scope that we define here as this variable scope wrapping the decoding. So decoding scope. Then next variable is going to be weights underscore initializers. So that's the TensorFlow argument name of this fully connected function, weights initializers, and that's of course equal to our weights that we just initialized here as a truncated normal distribution with standard deviation of 0.1. So weights, then naturally comes the biases, but underscore initializer to respect the TensorFlow name, biases initializer, and that's equal to our biases that we initialized as zeros, biases, and that's it. That makes our function that, I remind, will create a fully connected layer, which will be the last layer of our recurrent neural network, the one of the decoder. And if you want to take a step back, you need to understand that this fully connected layers will get the features from the previous part of the deep learning model, the previous part of the neural network, which is the stacked LSTMs, and will return the final scores. And then using a logit, like a softmax method, we will return the final prediction, which will be the final answer. Just realized a little typo here, wait like that, and now we're ready to go. All right, so now the next step is to get our training predictions. And that's going to be very easy because we have the right function for this, which is not this time a function by TensorFlow, but a function that we made ourselves. And that's exactly the decode training set function that returned the output when decoding the training set. And that's exactly what we need right now. So I'm going to introduce a new variable here that will be our training underscore predictions, and that will be equal to what is returned by this decode training set function that we made. And therefore I'm calling this function decode underscore training underscore set. And now we simply need to enter all the arguments that we defined for this function. And so now I'm going to input them one by one very quickly. The first one is the encoder state. The second one is the decoder cell underscore cell. The third one is the decoder underscore embedded underscore input. The fourth one is sequence underscore length. Then the next one is the decoding scope. Next one, output function. Then the key prob parameter, and finally our batch underscore size. Great, so that gives us our training predictions. And now guess what we're going to do? We're going to get our test predictions, because we're going to do in the training some cross-validation that's going to keep separately 10% of the training data to test the model on its observations, but without using them back for the training. So that's for the cross-validation part, and also what we're about to make will be used to infer, to predict our ultimate predictions, that is the answers of the chatbot after its training. So there we go, let's get our test predictions, but just before that we have to take our decoding scope and specify that we want to reuse the variables that we introduced in this decoding scope. So that's important to do it. And now we're ready to get the test predictions. And therefore I'm introducing a new variable here, test underscore predictions. And this time we will get them with the second function that we made, which is the decode test set function. And that returns exactly the test predictions. So let's call this function right now, decode underscore test underscore set. And again, we're going to input all the arguments that we defined for this function here. That is all these guys here. I'm going to input them one by one efficiently. And so feel free to inspect the decode test set function if you need more information on what we made before. So decode test set, the first argument we need to enter here is, like for the decode training set function, it's the encoder state. Encoder underscore state. Then next one, the decoder cell. Decoder cell. Next one, be careful, it's not going to be the decoder embedded input as for the training set, but I highlighted that in the previous tutorial. It's going to be this time the decoder underscore embeddings underscore matrix. All right, then next argument, it's going to be the key identifier of the star of string token, which we're going to get with our word to int dictionary. And now we need to enter the key of this token, which is in quotes and these symbols here, SOS, and that will give us exactly the key identifier mapped by the word-to-in dictionary. And I'm going to copy this because our next argument is going to be the key identifier of this time, the EOS token, the end of string token. Then our next argument will be the sequence underscore length, but -1 to not include the last token as we did before. All right, then next argument is going to be the total number of words, which we get thanks to our argument numWords. Then it's going to be our decoding scope, which we introduced at the very beginning of this decoder RNN function, decoding scope, and then almost over, we have 3 arguments to go. The next one is the output underscore function. Then it's going to be the keep underscore prob dropout parameter. And finally, the last one, we always end up with this one. It is the batch underscore size. We are always working with batch of inputs. That's a key element to apply here when doing deep learning. All right, batch size, that was our last argument. Now let's do a quick check to see if everything's all right. I'm seeing another typo that I made in this output function code subsection. It doesn't take an S here, wait with an S, initializer with no S. All right, and the same should be fine. So now what we're gonna do is get rid of these 2 warnings here, because basically they tell us that we haven't used training predictions and test predictions, so it's time to use them. And to use them, there is nothing more simple, because the exact thing that we have to do now, and be careful to go back to the width level and not inside the width. Right now what we have to do is simply return our training predictions and our test predictions, and there we go, we are done with the decoder RNN function. So now I think everything is all good, so we can select the whole code section to define effectively the decoder RNN function. And there we go, it's now in the console, it's defined, so we are ready to build our final sec-to-sec model. So congratulations, we just made the decoder RNN function that builds the recurrent neural network of the decoder. And so now I have some excellent news for you. We are ready to assemble everything, that is basically the recurrent neural network of the encoder and the recurrent neural network of the decoder, to form the final sec-to-sec model. And that's exactly what we'll do in the next tutorial. Until then, enjoy DeepNLP. Hello and welcome to the final round of this part 2, building the sec-to-sec model. We now have all the tools that we just need to assemble to build this final sec-to-sec model, and that's exactly what we're gonna do. In this tutorial, we will just use the previous tools we made, like, first of all, of course, the encoder RNN, which is the first main part of the sec-to-sec, then the decoder RNN, which is the second main part of the sec-to-sec, and that we made thanks to these 2 functions here, decode training set and decode test set, which we won't have to use again because these were just used to make the decoder RNN, the decoder recurrent neural network. So basically, we will just assemble these 2, encoder RNN and decoder RNN, and that will be our final round for this part 2, building the sec-to-sec model. So let's do it. Let's make this final function that we're going to call sec-to-sec underscore model. All right, it's the final ultimate model that we will chat with during our testing phase in part 4. Basically, you got it. That's the brain of our chatbot. All right, so this brain is going to take several arguments. The first one is going to be the inputs, which are of course the questions of the Cornell movie corpus dialog dataset. And after the training, these inputs will be of course the questions we'll ask to the chatbot when we chat with it. So input, then target. So that's of course the answers, the real answers that we have, because in our Cornell movie corpus dialog dataset, we have the real answers of the questions. and from which we will train the chatbot to speak. So that's the target. And then we have all our other arguments that we've used before. So the third one is keep prob. Then we have the batch size. Of course, we're working with batches, as always with deep learning. Then sequence underscore length, sequence length. Then we're gonna get our answers num words, which is the total number of words in all the answers. So that's like our previous argument that we used before, num words here. But this time, since we're gonna use both the total number of words of the answers and the questions, I'm specifying answers here. And in the next argument, actually, I'm gonna specify the questions underscore num underscore words. So that's another argument. Answers num words and questions num words. All right, then what do we have? Then we have the encoder embedding size. And that's the number of dimensions of the embedding matrix for the encoder. And then, of course, we'll have also the decoder underscore embedding underscore size, which is this time the number of dimensions of the embedding matrix of the decoder. All right. Then we have, of course, the RNN size, which we used before. Then the number of layers in our decoder cell containing the stacked LSTM with dropout applied, num layers. And then almost done, we have a final argument to input, and that's our questions words to int dictionary. Our questions words to int dictionary, which we'll use to pre-process the targets. Remember, if we have a look again at our pre-processed target function right here, pre-process targets, well, it takes word to int as one of the arguments, which is the dictionary. And so the dictionary we'll use here will be questions words to int. All right, so we are done with the arguments. That was the last one here, questions words to int. So let's add a colon here, and then let's go inside the function. So this function is supposed to return in the end the training predictions and the test predictions. That's basically what we've returned before, but we want an all-in-one package, which is the sec-to-sec model that will return at the same time the training predictions and the test predictions. And therefore, that's why the best word to describe what we're doing right now is assemblage. Like the French word, we're going to assemble the encoder that returns the encoder state and the decoder that returns the training predictions and the test predictions. But we also need the encoder, of course, because in order for the decoder to return the training predictions and test predictions, it needs to take as input the encoder states returned by the encoder. And that's why we need those two networks here, and we actually need to start, of course, with the encoder. But before we get the encoder state, we need the encoder embedded input. And that's why the first thing we have to do here is to introduce the encoder embedded input. We've already seen this variable, and this, our embedded input, and again I will put the resource for you to see how it works. We're going to get it from the embed sequence by the layers module of the TensorFlow library. I'll put that in the resource, and therefore what I'm going to do now is take first TensorFlow, TF, then contrib, of course, as usual, and then from contrib I'm getting this layers module. And from this layers module I'm getting the embed underscore sequence, which will return the embedded input of the encoder. And this embed sequence function takes several arguments. The first one is our inputs. Of course, that's the inputs we actually want to embed. So that's of course one of the arguments. Then the next argument is going to be the total number of words of the answers. So that's answers num words. And then we need to add a +1 because the upper bound in the sequence is excluded. So answers num words +1. Then the next argument is going to be the encoder embedding size, which I remind is the number of dimensions in the embedding matrix of the encoder. So encoder embedding size. Then next one, that's going to be the initializer, which is going to be a random uniform initializer. And to get it, we're actually going to use TensorFlow, and from TensorFlow we're going to get the random uniform initializer function. And this function takes two arguments, the bound of these random numbers we want to get based on a uniform distribution, and these bounds are going to be from 0 to 1. All right, so we got our initializer, and that's it. That will give us the encoder embedded input. So again, if you want more details on this embed sequence and its arguments, check out the resources of this lecture. Perfect. Now let's move on to the next step, which is to get our encoder state. I remind that the encoder state is what is returned by the encoder, that is the output of the encoder, and what will become the input of the decoder. So that's the natural next step, to get the output of the encoder, and we can actually get this output, the encoder state, thanks to our encoder embedded input. So let's get it, encoder state, which we will get from, of course, the recurrent neural network of our encoder. We're going to feed the recurrent neural network of our encoder with the encoder embedded input, and it will return the encoder state, which will then become the input of the decoder. So encoder state, then we get our encoder underscore RNN, the recurrent neural network of the encoder, which is a function we defined previously, and that function takes several arguments. The first one is, of course, well, our encoder embedded input. That's basically the input of the encoder embedded in the right format to be accepted by the neural network. Encoder embedded input, and then a couple of other arguments, the RNN size, the number of layers, then the keep prob, because of course in the encoder we have the encoder cell, which is a stacked LSTM with dropout applied, so we have to include this keep prob parameter that controls the dropout rate, keep prob, and now one final argument in this encoder RNN function. You can have a look at the function we made again, but if you remember well, the final argument is sequence underscore length. Alright, and now we got our encoder state, which is the output of our encoder recurrent neural network. And now that we have the encoder state, we are ready to get soon our final predictions, the training predictions and the test predictions. But before that, we need to get first the pre-processed targets, because we will need them for the training. We also need to get the decoder embeddings matrix, which is the embeddings matrix of the decoder, and that will be used to get the decoder embedded input. And then that's where we'll be fully ready to apply the decoder RNN function, which represents the recurrent neural network of the decoder, to get the final training predictions and test predictions. Alright, so let's get all these before we take our decoder RNN. The first thing we need to get here is our pre-processed targets. That is our targets pre-processed the right way to later on in the training use it to backpropagate the loss between the predictions and the targets. So pre-processed targets, and these, well, remember, we made a function for that, which we called pre-process targets, and this function takes several arguments. The first one is, of course, our target, because that's what we want to pre-process. So targets, then to pre-process these targets, remember I showed that to you at the beginning of the tutorial, we need the questions words to int dictionary. So that's our second argument, word to int dictionary, questions words to int, and eventually the batch size. All right, so now we have our pre-processed targets. Perfect. Now what we need is the decoder embeddings matrix, the embeddings matrix of the decoder. And so I'm introducing here this new variable, decoder embeddings matrix, which we will get by creating a TensorFlow variable. So variable is a class, and therefore the decoder embeddings matrix will be an object of this variable class. And this variable class takes several arguments, which are going to be mostly the dimensions of this embeddings matrix. So remember how the embeddings matrix works? Well, you have basically all the words in lines, and then in columns you have the embedding values. So since the number of lines corresponds to the total number of words in the whole corpus, well, this number of lines is going to be the questions num words, that is total number of words of the questions, and again we'll need to add a +1. And then for the number of columns, the second dimension, well, it's going to be one of the arguments of this sec2sec model function, which is the decoder embedding size, the embedding size of the decoder. So basically you can have several sizes for the embeddings, that is several number of columns, and that is determined by the embedding size. And so right now what we have to do in this variable is initialize this matrix, not only setting the dimensions but also fill it with random numbers taken from a uniform distribution just to initialize it, and then it will be of course populated with learning numbers that will participate into the training of the chatbot to speak like a human. But at the beginning we have to initialize it with random numbers taken from a uniform distribution. And to get these random numbers taken from that uniform distribution, we're going to use TensorFlow, of course, and then the random uniform function. Random uniform function, which will take as arguments the dimension of this matrix. And the dimension of this matrix, we'll have to enter them in square brackets. So as we said, the number of lines is going to be the total number of words in the questions, because each line corresponds to a token, a questions word, and therefore the number of lines is going to be here questions num words, and as we said, +1. Questions num words +1. Alright, so that's the number of lines, the first dimension. And then for the second dimension, that's the embedding size, which is one of our arguments. And that's, of course, for the decoder, so we'll get the decoder embedding size. Great, and so now we get out of these square brackets. We're done with the dimensions, but we'll need to add two more arguments, which are going to be the lower bound and the upper bound of those random numbers that we're filling this matrix with. And so we're going to fill this matrix with random numbers from 0 to 1. And all these random numbers will be taken from a uniform distribution. And that's it. That initializes the embeddings matrix of the decoder with random numbers between 0 and 1 taken from a uniform distribution. Great, now we're ready to move on to the next step. And the next step is, naturally, to use this decoder embeddings matrix to get the decoder embedded inputs. We're actually going to get these inputs thanks to the embeddings matrix. And so let's introduce this new variable, decoder embedded input, and we're going to get these inputs from a function by TensorFlow, which is taken from the NN module, and the name of this function taken from the NN module is embedding lookup. That's the function, embedding lookup. And this embedding lookup is of course going to take as input the decoder embeddings matrix. So I'm going to copy that to avoid any typo. Copy, and that's going to be our first argument in this embedding lookup function. Alright, and then the second argument that this embedding lookup is going to need is, of course, the preprocessed target. Because in order to get our decoder embedded input, we need the preprocessed targets as they are the answers to the questions. So let's do it. Let's add this second argument, preprocessed underscore targets. And there we go. We now get our decoder embedded input, which means we are ready to get the training predictions and the test predictions. And the reason for this is that we have everything we need to apply the decoder RNN function. That is, we have everything we need to feed the recurrent neural network of the decoder. And therefore now we're going to get our two ultimate variables that will be returned, which are our training predictions and our test predictions. Our training predictions and our test predictions, which are respectively the predictions of the observations used for the training and the predictions of new observations that won't be used for the training and that will either be used for cross-validation to test the predictive power of the model on new observations that won't be used to train the model more, or some new predictions just to chat with the chatbot. Alright, so make sure to understand the difference between these two predictions. And so now we're going to use our decoder because we have all the inputs we need to feed the decoder. So we're ready to get the output of the decoder, and therefore we were ready to get the decoder RNN, the decoder recurrent neural network. And so now, very easily, we're going to just input all the arguments of this decoder RNN function that we made, starting with the decoder embedded input that we just prepared here, thanks to the decoder embeddings matrix. So decoder embedded input. Then next argument, that's going to be actually the decoder embeddings matrix. Then we're going to need, of course, the encoder state, because this is actually the output of the encoder that becomes the input of the decoder. And so let's get it, encoder state. All right, then next argument is going to be the total number of words of the questions, which we get with the questions num words argument. Then we're going to need the sequence length, and after that the RNN size, then the number of layers in the stacked LSTM, then our questions words to int dictionary, then our keep prob parameter controlling the dropout rate, and eventually, last but not least, the batch size. Alright, and congratulations for your very last step of this part 2 building the sec-to-sec model. It's of course to return the training predictions and the test predictions. Alright, congratulations, you completed part 2 building the sec-to-sec model. So now your chatbot has a brain, it's time to train it. We'll do that in part 3, training the sec-to-sec model. I can't wait to start, I can't wait to teach our chatbot how to speak now that it has a brain, and we'll do that starting from the next tutorial. And now I'm gonna close this part 2 on a good note. I am gonna get our sec-to-sec model. Here is your brain, time to train it, and until then, enjoy DeepNLP. Hello and welcome to part 3, training the sec-to-sec model. We just built a brain in the previous part 2, building the sec-to-sec model, and now it's time to train this brain in this part 3 to make it smart, or at least able to talk, able to chat with us. So, for this tutorial, everything's going to be fine. We're going to set some values for the hyperparameters that will be used during the training, obviously, and that you will be able to change if you want to experiment more and try to improve the results. I remind that machine learning, deep learning, AI, and also of course DeepNLP, a lot of the work is experimentation, tweaking the parameters to try to find the best model that will lead to the best accuracy and eventually, in our case, the best chatbot. So we're going to choose some values here. I'm not saying these are the best values. At the end of this course, we will actually try to improve the model by either tweaking the parameters or improving the data preprocessing or even improving the architecture of the sec-to-sec brain of our chatbot. But these are at least relevant values that are most of the time the values used in the architecture of the neural networks you can find online. So let's do this. Let's set these parameters, and we're going to start with the number of epochs. So I remind an epoch is the whole process of getting the batches of input into the neural networks, then forward propagating them inside the encoder to get the encoder states, then forward propagating the encoder states with the target inside the decoder recurrent neural network to get the final output. First the final output scores, but then the final answers predicted by the chatbot, and then back propagating the loss generated by the outputs and the targets back into the neural network, and updating the weight towards the direction of a better ability for the chatbot to speak like a human. So an epoch is basically one whole iteration of the training. And we're going to choose 100 epochs. However, if the training takes too long on your computer, well, I recommend to choose less epochs, like 50, but not too low, because we really need a lot of epochs to get some correct results. So epochs equals 100, then we'll take care of the batch size, and we'll choose a batch size to start with of 64. And again, if the training takes too long, you can try 128. This will get basically more questions and target answers in your batches to train the neural network. So batch size equals 64. Then we have to choose a value for the RNN size, the size of the RNN, and we'll choose 512. Then the number of layers. The number of layers, which is how many layers you have in the encoder recurrent neural network and also the decoder recurrent neural network. So number of layers, and we're going to choose 3 layers. It's 3 layers, and we'll probably change that at the end of the implementation when trying to improve the model. So num layers equal 3. Then we have to choose the encoding embedding size, which I remind is the number of columns in your embeddings matrix. That is the number of columns you want to have for the embeddings values, where in this matrix each line corresponds to each token in the whole corpus of the questions. So encoding embedding size, and we're going to choose a size of 512, meaning that we're going to have 512 columns in this embeddings matrix. Then I'm going to copy this because our next hyperparameter is going to be not the encoding embedding size, but the decoding embedding size, for which we'll also choose 512. Decoding embedding size, then the learning rate, very important hyperparameter. The learning rate is quite tricky. We never know exactly what to choose. It must not be too high, it must not be too low. If it is too high, basically your model will learn too fast and will therefore not learn how to speak properly. And if it's too low, well, basically it will take ages for the model to learn how to speak properly. So learning rate, that's a tricky one. We're going to start with 0.01. I'll do a lot of experimenting, so make sure to check out, the checkpoint lectures, which are actually articles, but the checkpoint lectures at the end of each part where I share the code, because basically I give the last version of the code that I always try to improve. So in these checkpoint lectures, you will always have the best version of the code with the best hyperparameters and the best improvements and the best corrections. Because at the time I'm speaking, this is the first time I implement this, and therefore you can imagine that by trying to improve it and improve it and improve it again, well, the code and therefore the chatbot will definitely improve over time. So I'm starting here with a learning rate of 0.01, but don't be surprised if you find another learning rate in the implementation given in the checkpoint. So learning rate equals 0.01, and now we're going to have to choose a learning rate decay. So that's basically by which percentage the learning rate is reduced over the iterations of the training, because we want to start with a certain learning rate, but then we want to apply a decay over the iterations of the training to reduce the learning rate so that it can learn in more depth the logic of human conversations, in our case, or in general, the correlations identified in the dataset. So learning rate decay, very important parameter as well. And we're going to choose a common value that you will find in most implementations. We're going to choose a decay of 90%, 0.9. If you look at the implementations on GitHub or on any other open source platforms, you will either find a decay of 0.9 or 1, meaning that there is no decay. But we're going to apply a decay here, which will be 90%. Then next hyperparameter is a minimum of the learning rate we want to apply, because since we're applying a decay, the learning rate will be reduced over the iterations, and we have many iterations, so we don't want the learning rate to reach a too low value, and for this we're going to set a minimum learning rate. And this hyperparameter for that will be min learning rate, which we will set to be equal to 0.0001. So that's a very low minimum learning rate, but at least the training will end for sure. And besides, we will try to add some early stopping in case there is literally no improvement during the training. So no worries, with that and early stopping, the training will come to an end. And finally, we have one last hyperparameter to include here, which is the key prob hyperparameter. And for this, I'd like to show you something. So I'm going to go to Google now, and the thing I wanted to show you is this paper by the best of the best, Geoffrey Hinton. Geoffrey Hinton is the guru of artificial intelligence. He is the top one reference in deep learning, artificial intelligence, and all the research around it. And actually, the new, very promising capsule networks are invented by Geoffrey Hinton. So this is a paper by Geoffrey Hinton called Dropout, a simple way to prevent neural networks from overfitting. And we are going to trust the value recommended for the dropout rate in this paper. If we scroll down a little bit, well, first you have some nice explanation on what is the dropout, and especially here, you see when applying dropout, the neuron is present with a certain probability p, which is of course our key prob probability, the parameter that controls the dropout rate, but mostly that is equal to 1 minus the dropout rate, and that is for the training time. That is, we only deactivate the neurons with the probability 1 minus p during the training time, and then at test time, of course, all the neurons are always present. That's why, remember, when getting our test predictions, we didn't apply dropout. That's because the neurons are always present. So basically, this keep prob parameter is 1 minus the dropout rate. It's the probability of a neuron to be present during the training. And so if we scroll down even more, we will find a recommended value for this dropout rate. Right here, page 1933, we see that dropping out 20% of the input units and 50% of the hidden units was often found to be optimal. So this keep prob hyperparameter for which we have to choose a value is actually for the hidden units, not the input units. And therefore, we're going to trust Geoffrey Hinton for the first try of our model. We're going to choose a dropout rate of 50%, which therefore is a keep probability of 50% as well, because the keep probability is 1 minus the dropout rate. So that means that during the training, the neurons of our recurrent neural networks will be present with a probability of 50%. And we'll see how it goes, but I feel safe using Geoffrey Hinton's research results. All right, so let's go back to Python and let's include this keep probability hyperparameter. So I called it keep probability on purpose, instead of keep prob, because this is the name in the TensorFlow API, and therefore you must introduce it this way, keep probability. Keep prob won't work. So keep probability, and this we will choose, as we said, 50%, that is 0.5. And there we go. We are done with our hyperparameters. We could choose some more hyperparameters if we want to develop even more the models. These are not the only hyperparameters, but that's definitely the most important ones for our model. And again, feel free to tweak them. I will tweak them even more. I will do some research to try to improve the chatbot as much as possible. But for starters, these should be relevant values. Anyway, we'll test them in the end in part 4, testing the sec-to-sec model. So now let's select all these and execute. There we go. We now have our hyperparameters. And so we're ready to move on to the next steps. So the next steps are going to be quite quick and easy. We'll just basically prepare the training so that we are ready for it. That's going to be a big part. Try to get some good energy for it because we're going to have a quite long journey. Until then, enjoy Deep NLP. Hello and welcome back to part 3, training the sec-to-sec model. In this quick tutorial, we're going to define a TensorFlow session on which all the TensorFlow training will be run. So to open a session in TensorFlow, we're going to create an object of the interactive session class, and that object will be our session. But before we create this object, we need to reset the TensorFlow graphs to ensure that the graph is ready for the training. So in general, when you open a TensorFlow session to do some training, you have to reset the graph first. So we're going to start by doing this, resetting the graph. And to do this, we need to take the TensorFlow library and then apply the reset default graph function, which is a function by TensorFlow that resets the TensorFlow default graph. All right, and now we can define a session. And to define a session, as I said, we have to create an object of the interactive session class, and therefore we have to introduce a new object here, which we're going to call session, because this is going to be this TensorFlow session. And to create this object, we're going to take first the TensorFlow library because the class is from the TensorFlow library. And the name of the class is, as we said, interactive session. There we go, with some parentheses. All right, so we have defined a session. That's a good thing done. We will, of course, use it for the training. And now in the next tutorial, we're going to load the model input using our function model input that we defined in part 2 when building the sec-to-sec model. All right, so let's define the session effectively by executing the code section, and I'll see you in the next tutorial to load the model inputs. Until then, enjoy DeepNLP. Hello and welcome to this new tutorial. In this one, we're going to load the model inputs. That is, we're going to load the inputs of our sec-to-sec model. And to do this, we have a great tool for this, which we actually made ourselves, which is the model input function that we made in part 2, building the sec-to-sec model. That was the first one. This one here, that returns the inputs, the targets, the learning rate, and the key probability hyperparameter. And we chose a learning rate of 0.01, 1%, and a keep probability of 50%. All right, so we're going to use this function basically to return all these model inputs. That will be just one line, very easy. Let's do it. So the first thing returned by this function is the inputs. That's basically the questions that will feed into our sec-to-sec network. Then we also have the targets, which are the target answers, the answers to the questions. It's a target. Then the third element returned by this function is the learning rate, LR. And finally, the fourth and last element returned by this function is the keep prob parameter, keep probability. And all these four elements are the four elements returned by our model inputs function. All right, so let's get all these inputs by executing this line. And there we go, we have the inputs, the target, the learning rate, and the keep probability parameter. So another quick and easy step. Right now it's pretty calm, but then we're gonna have a storm when starting the big main part of the training, but no worries, we will survive it. So now I'll see you in the next tutorials to do some other quick steps, and then we'll start this main part of the training. Until then, enjoy DeepNLP. Hi guys, and welcome to this new tutorial. In this one, we're going to be setting the sequence length to a maximum length, which will be 25. If you remember, we already did that previously in actually part 1 data preprocessing at the end, if I remember correctly, in this sorting questions and answers by the length of the questions. Here we chose to go up to a certain sequence length, which was 25, and this +1 was just to include the 25 upper bound. But already by doing that, we set a maximum sequence length, and we have to do it again here to specify this on our sequence length variable, which is one of the arguments used by the functions of part 2. If we go to part 2, you see the encoder RNN takes as the argument the sequence length, as well as the decoder RNN right here, sequence length. So we have to basically set this sequence length variable now, and that's exactly what we'll do in this tutorial. So I'm introducing this sequence length variable, which is this time not an argument of a function like previously, but a real variable that we'll use later. And to create this sequence length variable, well, we're going to take TensorFlow, and this variable has to be inside a placeholder, a TensorFlow placeholder, like our model inputs. And therefore, I'm going to take the placeholder, but the placeholder with default function, because we're going to set a default value to produce when the output is not fed into the recurrent neural network. That's why we have to use the placeholder with default function instead of the simple placeholder function. So placeholder with default, and it's going to take as argument first the maximum length we want to have in the sequence, which, as we chose before, is going to be 25. So 25 maximum length. Then the second argument, as you can see, is the shape. And if you look at the TensorFlow documentation, you'll see that it corresponds to a TensorFlow tensor shape or a simple list of integers. And here, since sequence length is just a simple maximum length, there is no tensor to deal with, and therefore we'll just input none. That's the second argument. And then finally, the third and last argument is just the name we want to give to that sequence length. And we'll give the following name in quotes, sequence length. All right, sequence length simply so that we can reuse it afterwards when we need it for the training. All right, so that sets basically the maximum length of the sequences in the questions and the answers. This maximum length is 25, which means that in the training we won't be using the questions and the answers that have more than 25 words. All right, so let's execute this line of code. Execute, and there we go. We have our sequence length variable created that we'll now be able to use as one of the future arguments of our sec2sec model function. So that's a new step done. And now we're going to move on to the next step, another quick step before starting to get the training and test predictions, which is going to be to set this time the input shape. This is going to be very easy, and we'll do that in the next tutorial. Until then, enjoy Deep NLP. Hello and welcome to this new tutorial. Alright, so let's take a step back at what we've done so far in this part 3, training the sec2sec model. First, we set all the hyperparameters, and we chose a value for each of them, which is not our final decision, but some values for a first try. Then we defined a session here by creating an object of the interactive session class, and that will be the session used for the training. Then we loaded all the model inputs, including the input, the target, the learning rate, and the keep probability. And then just in the previous tutorial, we set the sequence length by choosing a maximum size of the sequence equal to 25, and that is because we're gonna soon use our sec2sec model function to get our sec2sec model, and since one of the arguments of this function is the sequence length, we needed to prepare this sequence length variable. And now, just before we're ready to use this sec2sec model function to get the training predictions and the test predictions, we just need to get the shape of the inputs tensor. Right now, our inputs are in a TensorFlow tensor, but we need to get the shape of these inputs because, again, this will be one of the arguments of one specific function we'll use for the training. This specific function is actually the ones function by TensorFlow that basically creates a tensor of ones, and the dimensions of this tensor is going to be exactly the input shape. So that's why we need to get it now. It's just because it's going to become the argument of this future ones function we'll use, just like what we did for this sequence length, which is going to be the argument of the sec2sec model function. All right, so let's get this shape of the inputs tensor. We're going to call this shape input underscore shape. And to get this shape, well, there is nothing more simple. We first need to get the TensorFlow library, and then we're going to use the shape function, which takes as argument a tensor and returns the shape of this tensor. And therefore, since the tensor we're dealing with here and what we want to get the shape of is our input, we will simply enter our input. And there we go, we get the input shape. Perfect. So let's execute this. Done, input shape created. All right, perfect. So now eventually we are ready to use our sec2sec model function to get our training predictions and our test predictions. And so that's exactly what we'll get in the next tutorial. And until then, enjoy Deep NLP. Hello and welcome to this new tutorial. In this one, we're going to do something very important. We're going to get the training predictions and the test predictions. So just to make sure you understand, we're not starting the training yet. That is the whole process of the training, and you'll see precisely when it starts. That's going to be from the moment we start the for loop over the epochs. But now we have to get the training predictions and the test predictions when feeding the model with the input we loaded in this specific line of code. So here we loaded the inputs, the target, which is what we need to feed the sec2sec neural network with. And therefore right now what we need to do is get the training and test predictions when inputting these inputs and targets and learning rate and keep probability into the neural network. So let's do this. The good news, you know what the good news is that we have the perfect function for this that will directly return what we want. And that function is, of course, the last function we made in part 2, the sec-to-sec model, which represents, of course, the whole sec-to-sec model, but as you can see, it's a function that returns in the end the training predictions and the test predictions. So this is going to be a very kid stuff tutorial. We're just going to use this function and input all its arguments one by one that we now made ready in the previous tutorials. Indeed, we prepared the sequence length, we have the batch size that was in the hyperparameters in the first code section of this part 3. We also have the keep probability, we have the targets and the inputs thanks to the model inputs function we got previously, and we also have all these parameters. Basically, we have everything to use this sec-to-sec model function and return the training predictions and the test predictions. So let's do this. It's going to be very easy. We'll just have to enter the arguments of the sec-to-sec model function one by one. All right, so since this function returns the training predictions and test predictions, very simply we're going to introduce two new variables that are going to be our training predictions and our test predictions. All right, our training predictions and our test predictions, not to be confused with the local variable in the sec-to-sec model function that we defined. This time it's the real variables that we will use later on in the training. So training predictions and test predictions that are going to be returned by our sec-to-sec model function. And now let's input the arguments one by one. The first one is the inputs. However, I noticed these are not yet in the right shape, and if you followed one of our other courses like the machine learning course or the deep learning course, I sometimes used the reshape function by NumPy to reshape the dimensions of a tensor or a NumPy array when working with NumPy to get it in the right shape for the model. And actually that's what we have to do here. The inputs so far are not in the right shape. So we're going to use kind of the same thing as the reshape function by NumPy, but since we're working with TensorFlow, this function is going to be the reverse function that is going to take the inputs. Let's not forget the parenthesis here. The reverse function that basically reverses the dimensions of a tensor. All right, but then remember in the reshape function by NumPy, we have to specify -1 and 1 to reverse the dimensions of this tensor shape. And in TensorFlow, we do it this way with a second argument here, which is going to be in square brackets -1. I will, of course, give the documentation of both this reverse function by TensorFlow and the reshape function by NumPy. So there we go with our first argument. So now let's move on to the second argument, which I remind is the target. All right, so there we go. Target, which we already loaded here by calling our model inputs function, target. Then the next argument we have to input is the keep probability, which is the probability of keeping the neuron activated during each iteration of the training. And we got this keep prob parameter at line 297 that we will later connect to the keep probability variable that we created at line 290, and that is a specific entity of the TensorFlow API. So we will connect that later, but what we have to input here in this sec-to-sec model function is make sure to understand the keep prob variable returned by the model input function and not yet the keep probability TensorFlow key. We will actually connect them later when running the session with the run method of our session object, and that will be in the big for loop over the epochs of the training. So keep prob, then the next one is the batch size. All right, always working with batches when doing deep learning, and we got our batch size here of 64, meaning that there are going to be 64 inputs and targets in each batch. So batch size. Then the next one is the sequence length, which we just got here, and then the next argument is going to be the length of our answers words to int dictionary. Then I'm going to copy this because the next argument is going to be the len of the questions words to int dictionary. So perfect. Then the next argument is going to be the encoding embedding size, which I remind is the number of columns in the embeddings matrix, each of these columns corresponding to an embedding value. And then again, I'm going to copy this because the next argument after that is going to be the embedding size of this time the decoding matrix, the decoding embedding size. All right. Then the next argument is going to be the RNN size, which we also got here in the hyperparameters, a size of 512. All right. And then two more arguments to go. The next one is the number of layers. And that, again, we got when setting the hyperparameters. Number of layers equals 3, meaning that there are going to be 3 layers in the cells of our recurrent neural networks, both the one of the encoder and the one of the decoder. So num layers. And finally, the last one, which is our dictionary. Questions, words to it. So basically now we're ready to execute this code section, execute to get our training predictions and our test predictions. Perfect. So now we're getting closer and closer to the big loop of the training, but we're not there yet. We have a few remaining steps to do, and we'll do them in the next tutorials. Until then, enjoy DeepNLP.